So my name is Jun Nakajima. I'm an architect at OTC, Intel Open Source Technology Center. I've been working on virtualization more than 10 years. And then Sainath, he couldn't make this, but he worked on lots of debugging stuff for this project. So anyway, I'll cover the entire session today. Okay. So this is about actually power of virtualization. If you run the kernel, the OS in virtualization, actually you can have more power to protect the monitor. And that way you can maintain high, integrity of a kernel. That's the point of this talk. Okay. So just want to quick this one. So first I talk about hardware-based virtualization, and then also the software that uses hardware virtualization, which is also called virtual machine monitor, okay, VMM. I will stay at high level because I don't think all of you are familiar with low-level virtualization stuff. So I'll keep high level. Okay. Then I will explain the ideas or our idea how we add the monitoring and the protection capability, okay, in virtualization. Okay. Then followed by the policy and then how we handle the events, incident upon some violation. Okay. Then talk about the architecture, the current architecture, and then based on our POC and the implementation. One thing I want to point out is this technique is applicable to both virtual machine and also bare metal. Okay. And for bare metal, actually, you don't need to pay the overhead of virtualization. You can still maintain a good performance of bare metal. I'll share the performance number as well. Okay. Then finally, I'll talk about more advanced topics beyond just kernel protection. Okay. So again, this is a high level, just to refresh your memory. Okay. So left-hand side, this is a typical bare metal OS where the operating system, single operating system, manage all the physical system and the system resources. Okay. Then on the right-hand side, you see the virtual machines with virtual devices running on top of VMM, virtual machine monitor. Okay. I'll talk about more detail on the next page. Okay. And in this case, multiple guests, the virtual machine will share the system resources. Okay. Now, if we look at the detailed virtual machine monitor, okay, typically, for example, like in case of Linux, the combination of a Linux and then the KVM becomes the virtual machine monitor, including QEMU. Okay. So what basically it does is it virtualizes for processor, memory, and I/O devices. Okay. So I have more. Now the question is, how can we extend, okay, or use this kind of software to add what we need, basically the protection and monitoring. Okay. So this is a high level of kernel protection. Okay. Basically, the idea is we extend the, I think it is this one. Okay. Processor virtualization, memory virtualization, and those to add those. Basically, for example, in case of memory, right, the hypervisor or VMM can actually write to protect some pages of the kernel pages, right, or data. Or the case of this one, hypervisor can lock the processor controls. Okay, I have more detail on the next page. And then also we can do the same thing for IOMMU. Okay. Now, what is the benefits? Why we want to use the virtualization? Okay. So in virtualization, actually, you have more power, like I said, right? You have a more monitoring capability, isolation, okay? And in fact, the Intel, for example, BT feature was initially intended for security enhancement. The virtualization came actually later, okay? That happened like more than 10 years ago, but I don't think this is a secret anymore, but anyway. So virtualization is pretty effective to add more security, okay? So again, hypervisor runs like, some people say it's a ring -1, right? Even it's lower than the native kernel, okay? Technically, we call virtualization root mode. So hypervisor itself runs in a virtualization root mode, and then the guests run in virtualization non-root mode, okay? The other thing we can do is we can virtually extend the CPU feature for security so that the kernel can harden itself to increase the security, for example, right? So that's the benefits. The other thing, in terms of implementation, you don't need to have all the code in the, you don't need to modify the guest. You can have a logic contained inside a hypervisor, okay? That would allow, for example, to change the behavior of the guest kernel, okay, at runtime. It's like a hot patch. But in case of a native case, you need to probably modify the bits, right, in the kernel, right? Otherwise, you cannot change that code path. But in virtualization, you can, for example, intercept the various events, for example, some attacks used by, kernel exploit is like divide by 0, okay? We can intercept that kind of exception in the hypervisor. Or page fault. If page fault happens in the kernel mode, we can intercept. And if you take a look at where it happened, then we can modify the guest behavior. Okay, so we can do that kind of thing. And like I said, this is also applicable to bare metal Linux. Okay, so the bare metal Linux can actually deprivilege itself to become virtualization non-root mode, okay? I'll have more details here, okay? So don't worry about it. So this way, if we run the Linux, bare metal Linux, in this mode, we can have additional security, okay, without incurring virtualization overhead. So this is good for, for example, running a bare metal containers with like HPC, okay, where you don't want to have any overhead, right? So this is more details. Or for example, I started with the memory protection, okay? So typically, if you look at the kernel implementation, kernel has read-only mapping, for example, for kernel text in a code, or some data. I have an example of read-only data of the kernel on the next page. So he wants to protect some pages, right? But the way the Linux can do is basically have a page table and set the permission as read-only, okay? This is actually a bit fragile, okay? For example, somebody, like a driver or even the bug, can change the permission of, the page table entry to make it writable, okay? That's one thing. Or somehow you can have different translation, mapping to the same page, but this time with writable. Okay, so in this case, if we use this translation, you can actually modify this page. Okay, but in virtualization, remember that the hypervisor has more power. Okay, so we need additional page table. Okay, that maps guest of physical. Okay, this one guest of physical address to host of physical, and that kind of page table is called like EPT, extended page table on Intel, and then on AMD it's nested page table. Okay, and they have additional permission. Okay, so if that page table says it's read only, even the guest had actually this way. Yeah, if guest had write permission, this read only actually wins. So the guest cannot modify. Okay, actually causes VM exit called the EPT violation. Okay, then go jump to the basically the switch to the hypervisor. Okay, so this is one example. Example of kernel read-only data. For example, like I said, the kernel text, right? The kernel, code. You don't want to modify it, right? And then some data structure. For example, some portion of a page table that actually mapping the read-only. Okay. If somebody tried to change the permission, right, page table itself, then you will change, you can change any translation in the kernel. Okay. Other thing is a system call table. Okay. Or the IDT, interrupt display table. Those are typically used for exploits. Okay. And there are more. And then if you look at the kernel code, you see this kind of thing. Okay. And those should be also read-only, but some people are not really sure, actually. We may break if we really restrict as a read-only. But anyway, from programmer's point of view, he thinks this is read-only, so we should, protect, right? Make sure this is not written or modified. If it's not, then the code is not really correct. The other thing is CPU control state. Okay, when the Linux initialize complete initialization, then he's set up the control state. For example, 64-bit paging and all the features available. Okay, what like security features. You don't need to know those, but those are, for example, enabling some security features. Okay. And then MSR is a machine-specific register that can affect the behavior of a platform or a processor. Okay, so once the kernel completes initialization and assumes some control state, and he continues to modify some bits in the control register, but for others, he really wants to fix those bits, and he doesn't want to change. Okay. If somebody tries to modify those bits, then it's probably bug or some attack. Okay. And I already covered this one, security extension. And one example is so-called the IOMMU, and I think the Palo submitted a patch. But this is one example. So today we don't have the processor that supports this one, broadly available, okay, in the market that supports this processor. Okay, but in virtualization, actually, we can implement this kind of advanced feature even on current processor or old processors, because we already have a VMX features on all the processors. So that way, the current or even old processor can take advantage of this feature, security feature. What the UMIP does is basically prevent the user level to execute some sensitive instructions, for example, exposing IDT, interrupt distributor table. Okay. Today, I say it's mostly, but this is good enough if we use existing BMX feature. Okay. Oh, then power virtualization. So if somebody comes up with very smart security feature, okay, that doesn't exist in real hardware, then you can implement that kind of a feature virtually in hypervisor and expose to the gas as a power virtualization. Then you can, for example, improve the security of Linux, okay, with kind of cooperation between the guest and the hypervisor. Okay. So this is IOMMU. I don't want to talk, cover the lots of detail. Probably Alex will like this, but the same thing is IOMMU. So when I think Alex talked about IOMMU, but in IOMMU there are some basic structures, and some of them are static. Once initialization is done, okay, the kernel doesn't expect they'll be modified, okay. Or the features he detected enabled, okay. If somebody is trying to turn off or some mistake, that's also bug or mistake or attack, okay. This is an example of how we specify the policy and handling, okay. So we specified asset. When I said asset means like a system resources, like the bits in the control register, MSR, port, or the guest physical address, okay? Or, so then a permission, like a read only or execution only were not available, and an action. So when somebody is trying to, for example, virus this thing, then the hypervisor needs to take some action. And at this point, what we have is basically ignore. Okay, so basically don't change for example, if that's a control register, don't change that control register. Okay, or allow. Okay, but the log, that kind of thing. So this is this still kind of a early stage. I appreciate your feedback. How we're gonna set up or the interface between user. Now I'm talking about the architecture. So this is, first of all, this is a KVM guest only. This should be simple, right? This is what's happening today, okay? Like I said, guests are running in virtualization non-root mode. This is part of an architectural state of the processor, okay? And this is what's happening today on the KVM, okay? Now, what we do is basically extend the KVM to monitor and to protect a specific part of the kernel or the CPU, virtual CPU resources, or IOMMU. Okay, so this is what's happening today, what we are adding. Okay. Now, with host, what happened is basically we extend the KVM, okay, to add platform protection. Okay. I'll cover more platform protection, but this is something like chipset or like BIOS or some sensitive hardware resources. Okay, we can also protect that kind of resources because that's a really physical stuff. Okay, then we call like this is a thin hypervisor. If you think of this as a thin hypervisor, okay. Then we deprivilege the entire Linux and then also the VM is still running VMX, the virtualization non-root mode. Okay, so this way, almost entire system runs in virtualization non-root mode. Okay, and then all the changes are integrated into the KVM. And for this, I'll have more details next, but it doesn't require QEMU. Okay. And you can deactivate or deactivate at runtime. Okay. And this is efficient. We use a so-called pass-through technique. Okay, I'll have more on the next page. Okay. So this page, this slide explains how we do this. So first of all, pass-through. Since for the bare metal, we don't want to, virtualize the actual platform. Okay, we use a pass-through. Basically, the bare metal Linux just access I/O devices, interrupt controller, timer, power management, those without causing any VM exit. Okay, it's basically native access. Now, for the memory area, this is also virtualized, but we use identity mapping. What it means is guest physical address is same as host physical address. Okay, so no translation, but we add protection, permission to this one. Okay. So if you look at the memory overhead, only thing you need to pay is additional memory for EPT, and this is just one per system. So it doesn't increase as you have more gas. So it's basically fixed cost, and it's small. And then platform protection. Like I said, for example, in the platform, you have a chipset or, memory controller, some setup for the BIOS, those kind of thing. Okay. And if you run, for example, container, right, you don't want the application in a container to access, based on some security for example, right? You really want to catch and prevent. I'm checking a time. Oh, start. Okay. So there's one problem. It's not really problem issue. We need to solve to maintain good performance of KVM. Okay. The problem is the KVM is not available in virtualization non-root mode. Okay. Unless you use nested virtualization. Okay. And probably you don't want to use nested virtualization for various reasons. One of the reasons is the performance, right? And this basically explains how we solve that problem. Okay. So what we do is whenever the kernel runs, like user runs here, no problem, but he wants to go across this one to use KVM. Okay. In this case, we need to go back to the virtualization root mode. Okay. To that end, we need to generate VM exit, right? There are tens of instructions that causes a VM exit unconditionally. Okay. The VMX off is one of them. Okay. If you execute VMX off in virtualization non-root, that automatically unconditionally causes a VM exit and jump to the hypervisor. So in this case, we have thin hypervisor. Okay, again, that's a part of a KVM today. Okay, but it's a different handler, and that handler, the VM exit handler, basically does kind of IDET. Okay, I read to the next instruction after BMX off. Okay? So from kernel's point of view, it's basically kind of seamless. He see VMX off, just the code sequence, and just jumps to the next instruction. So nothing happened. Okay. Now this is the prototype implementation. How we did this. So basically, we added the new I/O control to KVM. Okay. Here, okay, which is a switch and exit. Okay. What it does is basically construct BMCS. BMCS is a virtual machine control structure. Basically, it has the guest state and host state. Okay. In this case, we set the host RIP. This is a instruction pointer. It's an entry point. When you enter VM, which instruction that the guest needs to execute first. Okay. So what we do is set this RIP, guest RIP, to the next instruction. Okay. So when the kernel does VM enter instruction, then just jump go to the next instruction. So again, from kernel's point of view, it's just a seamless, contiguously, execute the instruction stream. Okay, so it's very simple. And then this separate VMX handler does the monitoring and then protection for the bare metal Linux. About EPT, extended page table, we can construct in advance, or as an option, we can construct at the runtime as we get BMX EPT violation. Yeah. Any question? I can take a question if you guys. This is a bit complex thing, so if you okay. Use mic, yeah.
The switching back and forth from root mode to non-root mode, does that not in itself defeat the purpose of the security? Does that not create a hole?
We may have some hole when we switch to the KVM. Yes, so if KVM, if the attack is inside a KVM, right? If somebody tweak the KVM module, then yeah, it's possible. Yeah. But again, I think we can have the code is very limited, right? The small piece of code that changes from the guest to the host. So rather than having that the point every in the kernel, I think if we just focus on the one point, then switch between the guest mode versus root mode versus non-root mode, then I think we have a more confidence.
So basically, the thing you're trying to prevent is that somebody manages to get code execution or anything in CPL0, and then is able to break out onto the actual system using that, right? I mean, that's basically the thing you're trying to prevent. Now, if I'm in CPL0, I can just write code that basically constructs my own VMCS, and I call the same thing, and I basically have root mode. So if I know that I'm running on such a system, I don't buy any security. I completely agree.
Yeah, but once, for example, you get once you get into this mode, right?
Once you get into CPL0, that's all you need. You don't need to modify KVM at all. You don't have to care about KVM at all. Once either you do have a kernel exploit or you don't. If you do have a kernel exploit, then you don't buy additional security, except for the few parts that you managed to prevent beforehand, because you were able to trap read-only pages and stuff. But other than that, there's nothing that actually prevents things.
I want to come back to that moment after this one. Okay. Can you ask the question again? Yeah. So, okay. Before that, I want to cover the performance stuff. So we ran some, the micro bench, like LM bench. LM bench is good to detect all the, overhead. Okay. And 3 of them, the bare metal, and then the non-root bare metal, and then the KVM guest. And those are the system call, okay? As you see, there are some visible overhead with the KVM, okay? If you just run KVM. With the, this one, you don't see any difference between bare metal, okay? So we don't have, visible overhead with this one. Something we observed was this one, but this is kind of noise level. Well, so 1 point something. This is kind of the max latency or the overhead we saw. Okay. The major reason is, again, we're doing pass through, and then we only monitor specific areas today. Okay. So now I'm talking about the more advanced, use cases. So obviously debugging, right? You can monitor or protect some area, which means you can, you can do some debugging, focusing on some, for example, if you want to monitor if somebody is writing some area, then you can, write to protect and use this as a kind of debugger, okay? Other area is, in virtualization, we have more capability in hardware. The reason is we want to monitor the guest, more. Means, for example, the PLM, it's called a page modification logging. So this is not available in a bare metal system, but if you run the, OS in virtualization, the hypervisor can monitor which pages in a guest are modified. Okay. So this would be good to, monitor memory activity in a guest. Okay. Or you can get additional exception. This is the so-called virtualization exception, as you see the name. So on a native system, you don't get this kind of exception. But if you run that system in virtualization root mode, now you can get this kind of exception. Of course, the hypervisor enables this one. Okay. And the other thing is a hot patch, right? Like I said. And then intercepting exception. This is more like brainstorming. So, okay, so I'm not sure this may work or not, but many DOS attack actually use divide by 0 or page fault in a kernel. Okay, so if for example, your kernel has that kind of attribute, and how the kernel knows, right? But you don't want to reboot the system. In that case, you either patch the kernel, right? Or you can use discount sync, and this might be better because you can have the patch in a separate component, and for many cases, you may be able to avoid modification to the binary patch to the guest operating system, because we can intercept again, divide by 0 in hypervisor, and we can change the behavior. Okay. For example, we can modify that return value from the instruction. Okay. For some DOS attack, that may not work, but for some that may work. So depending on the bugs or the exploit, it may work. Okay. So the current status, okay? So we have been, the POC has been done, and the code is very small. It's like less than 1,000 lines of code. Of course, some are in assembly code, right? But it's small. And then again, this is containing a KVM module, okay? We are working on the policies and then actions, and then we're planning to share the patch with community, getting some feedback. And next step is, we're gonna send out some RFC with the patch. So that's a plan, okay? So if, you are interested in, debugging low-level stuff, this might be the good area, okay? Because if you run the bare metal kernel, okay, in virtualization, sometimes when we already have completed the debugging, but when we done this first, we never saw anything, right? Right after we, for example, start running the guest, then we lost the system, black screen. Of course, we completed that kind of thing. So if we really want to enjoy that kind of low-level debugging, this should be fun. Okay. So now I want to go back to Alex's question. So I didn't expect that question. So
I guess what it really boils down to is it feels a bit like a solution searching for a problem rather than a problem searching for a solution. And I'm just trying to figure out what the actual problem is you are trying to solve, really. As in, what functionality? I mean, I've seen the slide on, like, you're missing a few pieces where you can't trap certain things, but the fact that you can't trap them probably means that nobody actually asked Intel to actually have them trappable or have them recordable. So what is status quo missing in Linux, in just general Linux operating systems, that you do need for what use case that this enables you?
First of all, the goal is to keep the integrity of a kernel. For example, kernel has lots of assumptions, right? Kernel developers' assumption of a data structure. Some are read-only, or the setup that the configuration he said should be static. Right. If some bug or something happened and you really want to detect. Otherwise, debugging or solving would be, it's very complex.
So from at least my limited viewpoint, I don't really remember too many cases where you suddenly have a second page table that happens to point at kernel memory, which then happens to be read-write. Usually the bugs we have are either hardware issues, and well, that's what you have IOMMUs and stuff for, or you have actual like real hardware issues, like the thing where you just have memory bit flips, right? But this doesn't prevent memory bit flips. It doesn't prevent hardware going wrong. The only thing it prevents is a software bug, basically, that you then would modify kernel memory, and you can still modify kernel memory in some space that then is read-write. So if you are actually able to control a pointer, you could then point it to something that is read-write, and because that's read-write, you just have to find something that is read-write and executable, and I'm sure you will find something, and then you suddenly have all the root mode that you want again. If you have a malicious attacker, this won't prevent anything. It will only give you a certain, like a slightly tiny bit more confidence that nothing happens by accident.
Well, I think first of all, there are security. Making systems secure is not just a kernel, right? It should go across the vertical, and yeah, this scope is only kernel, and even the kernel it's some low level, right? And try to provide consistent view of the programmer. Okay, so basically helping a programmer. The other thing is we are actually adding more security features to the hardware. Those are available in virtualization. So I really want to, Linux developers, kernel developers, to take advantage of more advanced security features.
Okay, I think I slowly understand where you're getting at. You're basically doing the thing that AMD does with the encrypted virtual machines. You can authenticate yourself, and that only works on virtual machines, and so you want to be prepared when the time comes.
Well, that's the other thing, but yeah.
All right, makes sense. That makes a lot of sense. Cool.
Hi, I have a question, or maybe just a thing to better understand how you're doing it. You said that you have an identity mapping. So where do you put the hypervisor shim when you have an identity mapping? There must be some kind of difference between the bare metal memory layout and the identity mapping. So do you put it on the top of the memory, or where do you hide the look?
It's almost identity.
It's almost identity. And the next question is when you depromote or when you promote from non-root mode to root mode, does that mean that then the guest runs on bare metal? Or
You're talking about bare metal case or KVM guest?
When you start a KVM guest, you said there is the VM off.
Well, KVM guest will just continue to run in a KVM guest. The one I talked about was that for the bare metal case, right?
Can you maybe just go back?
This one or?
This one, yeah.
Okay.
When you
So this case is, for example, this IO control will be triggered by user mode, right? Then that program does this new IO control. So it's this one, okay? He does IO control, then, from there, once we do VM enter, then this kernel start running in a VMX non-root mode, then go back to user. So the user process, entire process, right, the system will start running in a VMX, virtualization non-root mode. So this is not a KVM. Again, this is a bare metal Linux.
Okay.
Yeah.
So have you thought about running KVM in the privileged bare metal Linux, like virtualizing VMX on, VMX off, and all that, so that you can still run virtual machines in this?
Nested virtualization, or?
Yeah, because it's much simpler than nested, because of course it's partially identity mapped. Like of the 3 layers of page tables, the outer one is identity, so you don't need shadowing. You can simplify a lot of things, actually. Probably more VMSCS field can be...
This one, right?
I don't know.
So you are saying... So in this case, this is kind of native, right, running on bare metal. And if we just go to this one without this doesn't happen, then we continue to run in the non-root mode, right? Then KVM try to do some, for example, VM enter, let's say, or then that generate VM exit.
Yes.
Right? So back to this, that's basically nested virtualization.
So my 2 questions about this are, first, performance, and second, whether you need to actually protect some VMCS fields, and how do you do that?
So the performance, the cost of this one, VM exit, is less than 1,000 cycle. It's actually lighter than usual VM exit because you just continue to, run, and you can optimize that processor state to save, right? You don't do anything. You just continue to jump to the next instruction. Yeah, so it's lighter than usual VM exit.
Okay, and do you can trap like the VM read and VM, VM write to shadow them?
Well, we can do that. So we can avoid this one, continue to run in KVM in virtualization, so nested virtualization. We haven't measured that, the kind of performance yet. But I think this is, more optimal or, solution.
Okay.
Yeah.
Cool.
Hi. So I think, if I understand correctly, the issue that was discussed security-wise before was that if an attacker can issue a VMX off, then the protection provides is not there. Security you can turn off is not secured at all. But do you think that there is actually a use case where you could have like OpenBSD's pledge where you say, I'm not going to issue any more VMCS management anymore, and you break the fuse?
Yeah, so this one, right, if we can change this behavior, at this point, this is you can go back and forth, but depending on the implementation of the hypervisor, if you allow only one transition for the life of the system, right, then somebody else tried a VMX off, then in that case, that's malicious because we only allow one-time transition, right?
I think that could have some applications when it's a static embedded device.
Yeah.
Great, thanks.
How do you handle multiple consumers of the VMX extensions?
Multiple consumers.
Yeah, like a VMware Workstation, for instance.
To run this on the VMware or?
No, if you're running VMware Workstation on this version of Linux.
Okay. Okay, so you're talking about additional. So you have some VMware driver in the kernel.
Yeah, additional driver that uses VMX extensions.
I think we can have this kind of thing as well. So initially we had this code in actually the context switch. So we make the part C groups for KVM. So when we enter the KVM, we do this. So we can, for example, tell that the kernel or the VMware driver, right, to cause this kind of thing. Then the VMware will get the native VMX, feature.
And will this require changes to their software as well?
I think I need to think about it.
Okay.
Or the other way is this happens per CPU. Okay, so you can run some CPU in virtualization non-root mode. Okay, and you can continue to run the rest as just native mode. In that case, if you bind those processes to VMware, you don't need to do anything.
So I had a quick question about PML. So I didn't quite understand what more information you're getting just because you're running the host in non-root mode. So PML still gives you the same amount of information, right?
Yeah, PML basically causes a VM exit if, for example, the number of the modified pages reach 512 or whatever number, okay? Then there's a logging which gets the physical pages modified, okay? So in that case, if you use that for the native kernel, bare metal kernel, then you can tell which pages have been modified.
But the bare metal kernel knows, you mean KVM will learn about the bare metal?
But to know, okay, so probably this way. Yeah. To know which pages are modified, okay, you need to go through all the page table or, somehow you need to write to protect.
The proc file system. I mean, something in the proc file system will tell you about what is idle, what's not, and so on.
I'm not sure you can effectively do that.
Okay. Maybe I think it's possible, but That's fine. This is another way to do it.
I'm talking about the physical memory.
Yes.
Okay, not the virtual address.
Yeah. But admittedly, this is another way to do it, yes.
Yeah. And then in this case, you don't need to work all the page table because page table has a modified access bit, right? And to find out which pages are modified, you need to go through all the page table hierarchy. But in this case, you have just a log. It's just a one-dimensional array, contains all the the page frame numbers. Okay, that way you can efficiently identify which pages are modified. Okay, I think I'm done. So this is the end of my presentation. No, right? No. Okay.